Okay, part two. The first time. I'm gonna repeat everything. Okay, this is my exam question for exam one of heat transfer. Question one, what's the difference between heat and temperature? Define each in your own words, then add an equation to show how they are different. The heat definition is transfer of internal energy caused by a temperature difference. Temperature definition, a property of material that depends on internal energy of the material. Any equations to show they are different. So we have Q is equal to Ka, change in temperature over change in time. Q is equal to Ha, change in temperature. Q is equal to Hi, area, change in temperature. And temperature and heat are different, but a gradient causes heat transfer. Calculate the heat transfer through the heat sink shown, assuming that the base temperature of the device that is mounted to it is 82 degrees Celsius and ambient air is 24 degrees Celsius. You choose to mount it horizontally. So we're given its resistance network for vertical and horizontal mount. We will be using the horizontal. We are given our dimensions and the surface area. So to find the heat transfer rate, we use Q is equal to change in temperature over R. We are given our two temperatures and we divide it by our given R, giving us a heat transfer rate of 48.33 watts. Question three, describe each of the terms and then all the terms in the equation below. So our first equation is heat diffusion in the direction of the angle. Our second part of the equation, heat diffusion as the angle changes. Our third part is heat diffusion in respect to z direction. For the fourth part is heat generation. And the fifth part is change in energy in respect to time. And then R is represented as the radius of the cylinder. K is our thermal conductivity. V is angle coordinate, typically in degrees. Sometimes can be represented as change in temperature. T is temperature. P, or is it phi, is density. Cp is our specific heat capacity, typically given either in the question or on a table. T is time. And then this is the heat diffusion for our cylindrical coordinates. Question four, cylinder wall has an inside radius of 100 millimeters, outside radius of 120 millimeter. Answer the following questions, assuming that the inside wall temperature is 212 Kelvin, the outside wall is 290 Kelvin, and the pipe is at a steady state without any generation within the solid. For this, we use our equation temperature surface, but temperature, natural log, radius 2, which radius? Yeah, radius 2, that's supposed to be a 10, sorry. Radius 1 over radius 2 divided by natural log of radius 1 over 1. I appear to have written this slightly wrong. Sorry, I was getting confused here. It is the temperature. So we have our 112 gives us here. So you have natural log of the given r over radius 2 divided by natural log of radius 1 over radius 2. Plug that in, you have 290 plus change in temperature, natural log 110 over, 112 over 120, since that is the radius trying to find the temperature at. That gives you a temperature of 298.33 Kelvin when the radius is 112 millimeters. Part B, assuming the pipe is 25 millimeters long, what is the heat transfer rate through the pipe, assuming thermal conductivity is 143 watts per meter Kelvin? So we use our heat transfer rate for a given cylinder. Q is equal to 2 pi length times K, change in temperature over natural log radius 2 over radius 1. Our length is 25, which is given. Our K is 143, which is also given. And then change in time, 312 minus 290, all over natural log of 120 over 100, giving us a heat transfer rate of 2.71 megawatts. Question 6. What is the resistance to the heat flow from a pipe buried underground to the surface of the ground? So the resistance of the ground between the pipe and the soil surface. The pipe is 20 meters in length with an outside diameter of 130 millimeters and is buried 2 meters underground. That's the distance to the center of the pipe from the surface of the ground. The soil has thermal conductivity of 0.52 watts per meter Kelvin. So we have to find our S to properly find our resistance, which is 2 pi L over natural log of 4ZD. To find that, we do our 3D over 2, plug in our given numbers, giving us 0.195, which is less than 2. And our S is 30.50, 33 meters. Plug that in. Our S is found above, and our K is given. So we have a resistance of 0.063 kelvins per watt, Kelvin per watt. Or 7, a heat sink is used to cool processors to a constant temperature such that the temperature at the base of the fin is 100 degrees Celsius and is made of aluminum. K is given. The heatsink geometry can be seen in the image below with units in millimeter. Air blown over the heatsink has the following parameters. Temperature of air is 25 degrees Celsius, and H is 35 watts per meter squared Kelvin. So H is also given. In the figure, it gives us the length and width. We convert this from millimeter to meter, and then square it. So that gives us the area of the base is 0.0025 meters squared. And then for the area of the fin, you do the same thing, 3.5, 3.5, and convert it to meter, giving us 1.225 times 10 to the negative 5 meters squared. For M, then we find our M. So we can find our QF. In our QF, we need to have our M. Our L is given, our H is given, our K is given. Our P is found to be 0.0149. Our K is given, and we've already found our AC, and then theta B is just the change in temperature or temperature difference. For that, we have HP over KHB, so that's the area of one fin. We plug in our numbers, and we're given 12.9. From there, now we plug in our given and found numbers into this long equation, giving us a heat transfer rate of 0.917 meters. Since that is just one fin, to find all fins, you multiply by 25, since there are 25 pins. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then you multiply them, giving us 22.926 watts. Part B, what is the heat transfer rate from the non-fin base area of the heatsink? So for this, we need to find the area, corrected area, which is the area of the base minus the area of the fins. So we'll take the found area of one fin, multiply it by 25 to get the total area of the fins, subtract the 2, and we get 0.00219 meters squared. From here, we plug in our heat transfer rate for convection of the fin or of the base, which is QB is equal to HA area base theta B. So H is given as 35. Our AB was previously found here. And then theta B is the difference in temperature, which is 75. Once multiplied, you get 5.758 watts of heat transfer. For question C, what is the total heat transfer rate from the heat sink? You combine the two. You have the heat transfer rate of the base and the heat transfer rate of the fins. Added together, you get 29.4 watts. Part B, the composite wall below has the following parameters. It gives us temperature 1, temperature infinite, all the needed heat transfer coefficients we need. Then we have our RTC, which is this gap here between 2 and 3. And then we have our areas along with lengths of the materials. So we initially draw our resistive network of the temperature, the flow of heat from temperature 1 to temperature 4, and then to temperature infinite. So we start at temperature 2, it goes through A, so that is represented as RA, then it gets to temperature 2, and then it travels through our RTC, which then travels to temperature 3, which splits parallel to resistance B, so part material B, C, and then it comes back together at 4, and then it is convection from the surface of T4 to the air. For this, we will use for our A, B, and C is all conduction for A, B, and C. So we have our 1 over Ka, which is given for A, B, and C, and then our lengths are also given. So it's a plug and chug. Sorry, length. It's length over Ka, not 1, because our length's 0.1, 0.1, and 0.2. From here, we have our resistance for A, B, and C, and then we find our resistance for convection, which convection is 1 over HA in this case. And then to find the resistance, for RTC, you take the 0.12, since this is R double prime, divided by the area of C, which is 0.7, giving you the resistance. When adding these up, we need to consider which resistors in this case is in series and which ones are in parallel. RA, RTC, and R convection are series, and then RB and RC are in parallel. So you add them accordingly to the rules for adding resistances, giving you an R equivalent of 0.254 Kelvin per watt. Or T was heat transfer from temperature 1 to temperature infinite. So we come back to our simple equation of Q is equal to change in temperature over R. So now we have to decide what temperatures and what resistances we will be using. For our case, we'll be using the R equivalent because we're going from temperature 1 all the way to temperature infinite. So in this case, our temperature 1 is given as 12, our temperature infinite is given as 21. So that will be our temperature difference, and then we will use the found equivalent resistance, giving us a heat transfer rate of 350. God, I suck at writing. Is that a 7 or a 2? It's a 7. 357.24 watts. Need to work on my penmanship here. All right. And part D, which is extra credit, but I had attempted it, so I am correcting it. What is the temperature at temperature 2? So we take our same equation, but instead solve for change in temperature because we know our Q and we know our R. Change in temperature becomes our initial temperature, 120 minus temperature 2. In this case, we will use the resistance of material A because as the temperature or heat as the heat transfers from temperature 1 to temperature 2, the only material it passes through is A. So we will use the resistance of A. One plug that in, I found Q, or found A, giving us the temperature at 0.2 is 106.9 degrees Celsius. Okay, that is my exam correction.